Hey, welcome back to The Explainer. Today we're diving into something pretty amazing, the secret language of our bodies. It's a language that's not spoken in words, but in electrical pulses, chemical reactions, and physical movements. We're going to explore how we can actually translate this hidden dialogue into information that can, quite literally, save lives. So, let's just jump right in with a question for you. What could your heartbeat and your favorite song possibly have in common? I know, it sounds like a weird comparison, right? But the answer is actually the key to understanding everything we're about to talk about. And the answer is, they're both signals. That's it. See, a signal is really just anything that carries information, showing how something changes over time. So whether it's the vibration of a guitar string making music or the electrical pulse from your heart muscle making a beat, they're both doing the same fundamental thing. They're conveying information. And the truth is, we are surrounded by signals. I mean, they are absolutely everywhere. The sound of my voice reaching you right now, that's a speech signal. The temperature in your room, the Wi-Fi that's connecting your device, all signals. But for us, the most fascinating and maybe the most important are the biological signals being generated inside our own bodies as we speak. And that leads us right into our first big topic, your body's secret language. We're going to take a closer look at these incredible electrical, chemical, and physical signals that our physiology creates, and more importantly, what they can tell us about our health. Here's the catch, though. Trying to listen in on this language, it's not so easy. The raw signals coming from our body are almost never clean and clear. They're usually messy, a bit chaotic, and buried under all kinds of interference. It's a lot like trying to tune into a radio station that's just full of static. The song is in there somewhere, but good luck hearing it. So, how do we cut through all that static? How do we clean up the signal so we can actually hear the message? Well, that's exactly what our next section is about, making sense of the noise, which is really our introduction to signal processing. Okay, so before a computer can work its magic, we've got to turn that natural analog signal into a digital one. Think of it this way. First, you have the raw, continuous wave from the body. Then we do what's called sampling. We take thousands of tiny little snapshots of it every single second. After that, we quantize it, which just means we give a specific number to each of those snapshots. And just like that, we end up with a clean digital signal that a computer can finally read and analyze. And this is where things get really interesting, because not all that static is the same. There's a crucial difference. You've got noise, which is interference from the environment. Think of the hum from a power line messing with your reading. And then you have artifacts, which are actually errors we cause ourselves, like if a patient moved just a little bit during an ECG test and the electrode shifts. Both of them mess up the signal, but they come from totally different sources. Now, a huge part of all this is just making the data manageable. And the source material had a perfect analogy for this. It's kind of like sending a picture on WhatsApp. You know how the app compresses that huge photo file to send it fast, but when your friend gets it, it still looks great on their phone? Signal processing does the exact same thing. It can shrink these massive piles of biomedical data, making them way easier to store and analyze, all without losing the crucial life-saving detail. All right, let's see how all this theory works in the real world with a perfect case study. The heartbeat, seen through an ECG. We're going to explore why its unique, rhythmic pattern makes it the classic example for biomedical signal processing. But here's the thing. Even with a strong heartbeat, the raw signal we get at first, it usually looks just like this, a complete, chaotic mess. You can maybe see a pulse in there somewhere, but it's totally buried under all that noise and artifact we were just talking about. A doctor can't use this for a diagnosis. No way. And that's where the magic of processing comes in. We use these really clever mathematical filters that can target and surgically remove the frequencies of all that unwanted junk. It's literally like cleaning a really dirty window. You just meticulously wipe away all the grime until you can finally see what's on the other side. And look at that. After all that processing, the chaos just disappears. And what we're left with is this, the clean, crisp, incredibly valuable ECG waveform. What we've done here is translate total chaos into crystal clear data, the kind of data that lets a doctor diagnose a heart condition and, yeah, save someone's life. And this isn't just some cool science experiment. This is real stuff with real consequences. And that brings us to the most important part, our final section, signals that save lives, where we get to see the huge real-world impact of this tech.
I mean, this technology is literally everywhere in modern medicine. It's crucial for diagnostics, right? Like an ECG finding the cause of chest pain. It's used for continuous monitoring in the ICU. It's the brain inside devices like pacemakers, telling them exactly when to work. It's probably in the smartwatch on your wrist right now. And it's the engine that drives so much research into the next big health technologies.
And we're not just talking in hypotheticals here. In fact, the source material had this incredible story about a woman who fell and was knocked unconscious. Her Apple Watch detected the fall automatically and immediately sent her location and her health stats to emergency services. First responders were able to get to her early. I mean, that is signal processing, in the wild, saving a life. So right now, we can listen to the heart, the brain, the muscles. But think about it. Our bodies are sending out countless other signals all the time. As our tech gets better and our processing gets smarter, it really leaves you with a huge, exciting question. Our bodies are constantly talking. What else are we going to learn to hear? Thanks for joining me.